Okay, if you're all happy with the protocol of things, what I'm going to give you to do today, so I realise you're all young, active minds. Who comes from an electronics background? Who's done a degree in something connected with, okay. Well, those of you who do come from an electronics background, I'm not going to insult your intelligence and you can run as fast as you want to, but we've obviously got to get a bit of theory under the belt for the ones that haven't. And one of the things that we're going to come across today is the classic potential divider. And you would be amazed how many circuits you will find that potential divider contained in. Absolutely amazed. Forms the element of most filters, and at the end of the day you can break a circuit down into just a series of potential dividers if you understand serial and parallel connections and so on. Okay? So if I've got this situation here, and let's just assume that this is a battery, we'll draw the proper symbol for a battery, yeah? If I draw a circuit like that, now there is a proof on the Moodle pages, if you want the proof. It's not very exciting, and doesn't really serve any great purpose if you can prove it, but you can if you want. I'm not going to do it here. And you've got R1, resistor 1, R2, resistor 2. If this is V in, which we'll say, what should we say, is 9 volts, yeah, because that's a little, one of those little square batteries, yeah. So what I want to know is what's V out. What's V out? What's the answer? Well, fairly obviously it depends what R1 and R2 is, right? Because if I'm at liberty to play about with the values of R1 and R2, I can control what V out is. Okay, so just giving the gain away, and I'll leave this on the board when we did start the simulation. Actually, the answer is V out equals V in R2 upon R1 plus R2. It's the potential divider equation. Incredibly powerful and incredibly simple. Because what it means is I can now replace this resistor with a reactive device like an inductor or a capacitor, and I can still use this equation to derive what the circuit's going to do. I'll do that next week. Let's keep it simple. Let's just have non-reactive. In other words, they're not frequency dependent. A resistor does the same at 1 hertz as it does at 1,000,000 hertz. It's not reactive. So R1 and R2, V out equals V in, R2 upon R1 plus R2. And you can plug the numbers in. So, an exercise for you, if I said 4.5 volts was what I wanted out, that'd be too simple, right? Because I think you can just see straight away that you'll drop half the voltage across one and half the voltage across the other. So, but how would you decide what R1 was? Because you could say R1 is 1 ohm, R2 is 1 ohm, you get 4.5 out. Would that be a good choice of resistor value? Why not? Because of the current. If I chose this one here to be 1 ohm and this one to be 1 ohm, there'd be a 2 ohm path going to ground, and I'd be using lots and lots and lots of power, and the current would be flowing, things would be getting hot. What a waste. Generally, you kind of start in around about the thousands of ohms, so 1k, 10k, 100k, those kind of sizes. Okay, so with that in mind, what I'd like you to do, and I'll give you 2 minutes to do this, 3 minutes to do this, What I'd like is I'd like V out to be 3.2 volts. Okay, off you go. I haven't got any sweeties today. I might bring some sweeties in for this type of thing. But what values, and let's assume that they're K's, thousands of ohms. What value of R1 and R2 do I need to get V out equal to 3.2 volts? I'll say straight from the start, you need to make an assumption. And that assumption is one of those resistors you've got to assume. Because without assuming one of those values, you can't work out the other one. So make an assumption. Make an assumption. Sort of assumption I think I would make, I'd probably say R2 is 5K. And then I calculate from there. I love giving problems because it all goes quiet, doesn't it?